Okay, year 12. Here's a little bit of feedback on the work you did for me for the photocell practical. This is where we varied the frequency of light hit into photocell and measured the change in stopping potential. Plotted a graph of stopping potential against frequency, and from the gradient, we've got the Planck constant. So I've had a look through all of your work. On the whole, looks very good. A few of you have had a few problems with plotting the wrong thing or incorrectly calculating the gradient. But I think we're all getting there in the end. But the important thing is all getting a value of a Planck constant to be actually quite close to the correct value, which is pretty good because obviously Planck constant is such a small number. Anyway, but let me just run through my observations. So yeah, we've got the graph. Well, this is my graph, okay, and just first thing, when we're plotting a line of best fit, okay, it's a straight line in this case, so it's y equals mx plus c. It's really important. Make sure that you zoom in as much as possible, okay, because it makes it much more easy to see where that straight line should go. So just I might be stating the obvious here, but it has to be through the middle of the point. Now it's these distances, these perpendicular distances of the points to the line, they have to be minimized as much as possible. Okay. Now, if you remember to zoom in on each axis, we go into settings or the spanner symbol, and then yeah, you can alter the range on the x-axis, the range on the y-axis, and it will scale it accordingly so that it spreads out. It's really important that we have these points spread out over the whole of the graph paper, and then you can zoom in and out at will. So you've got the scale perfect. We've got our line of best fit, and we've then got a value of both gradient and y-intercept. Okay, so very good. So yeah, I've seen most people's graphs. They look excellent. Just one thing: when you do a graph for me in Desmos, can you please share the actual graph with me? I'm seeing a lot of screenshots, which is nice. I can see that you've done it. However, I'd like to be able to zoom in and check the quality of your line of best fit. I can only do that by zooming in. Okay, I can also see very easily and quickly where you've gone wrong if you've gone wrong. So just to remind you to share, you just go to this thing here. So we're then going to share, right, and then just copy. You just literally copy the URL, right, and then you can put that, you can attach that, I think, to the assignment, or just include it as a URL in the text. Okay, so that would really help me enormously. So there you go. There's the graph. Okay, there's my graph. I was quite pleased with that because the analysis part. What do we get? Right, this was my analysis. Okay, just first thing, most important thing. Yeah, I've seen a lot of people's quite complex analysis. Can we write it out, please, on a sheet of paper? Write it by hand. I think because we've got an equation, because we have lots of powers of 10, because we have equations, by typing it in a Google Doc, it's making it too complicated. It's making it difficult for you, but it makes it almost impossible for me to actually read it properly. So this is what I've done. I've just written it out, taken a photo with my phone, and then just upload the JPEG. That's actually easier for you, and it makes it much, like I said, makes it much easier for me. Okay, right, the table. This is my table here. So, okay, so we've got the filter colors and filter numbers. Right, these are the wavelengths. Right, you don't have to write all the, because nano is 10 to the minus 9. You don't have to write 6.51 times 10 to the minus 9, 5.86 times 10 to the minus 9. You don't need to do that. Doesn't have to be in standard units. Just write nanometers in the column header. Okay, and then we can just key in the easy numbers. Now, for the corresponding values of frequency, again, you don't have to write 10 to the minus 14 next to each value. right? You do exactly what you would do with the unit. You put it in the column header only. That makes it much more easy to compare two values with each other. Okay, so any powers of 10 is up in the column header with the unit, please. And then we've got the values of stopping potential. And so my analysis, okay, there's just it's always nice to put that in the analysis to justify what you've plotted and how you're going to use the gradients. Okay, so and that gives me, with my line of best fit, I got a value of Planck constant to be 5.76 times 10 to the minus 34 joule seconds, right? This is probably the thing that annoyed me most from looking through all your work with this, with practical, is the lack of units. Please, it's absolutely crucial. Everything you do in physics, especially when you're writing down a final value, if you don't include the unit, the correct unit, all your work has been a waste of time. It's literally that simple. Okay? This is a practical task. The units, like all calculations, are absolutely essential. Please, can we just step it up with the rigor with regard to units, please, that we need to be showing. Okay. Always, I think it's always good if you are finding a value from a gradient and you know the true value, always quote it in your analysis. Yeah. And say, well, the actual value we know is 6.63 times 10 to the minus 34 joule seconds. Okay. Y-intercept. Okay, I got minus 1.565. So obviously, yeah, this thing here, the y-intercept is minus psi over e. That gives us a psi of 2.504 times 10 to the minus 19 joules. Now, how much electron volts is that? What's that number? Divided by 1.6 times 10 to the minus 19. So it's actually this number. This is the value of work function in electron volts, 1.565 electron volts, which, if we remember from the last lesson, because a cesium antimony metal plate, it should have a work function around about 1.65 electron volts. So that's pretty close. I'm happy with that. It looks like it's the same percentage out that our Planck constant is. So that's fine. That's fine. Okay. So just one last thing to talk about then is, okay, percentage difference. Like I said, if you're going to quote the final value and the known value, then work out your percentage difference. Okay, dead straightforward. Now, because the calculated value and the known value are both 10 to the minus 34, we don't have to include that in the calculation for percentage difference. So we're going to go, okay, the percentage difference in the values of Planck's constant is, so it's the known value, 6.63 minus 5.76 over the actual value. So actual minus measured over actual. And that comes out at about 13%, which is brilliant for this kind of practical. I think that's pretty cool. Okay, so but it's still significant. 13% is still significant because all of the points look to be very close to our line of best fit. So there must be this. Okay, if all your points are pretty bang on a straight line of best fit, but you're still out by a significant percentage, that suggests that you have a significant systematic error in your practical. Now remember, a systematic error is something that happens. It's an error or something that gets added on for every measurement. So What could the systematic error be in this setup, do you think? Okay, well, the first one, I think I've discussed this in the first video, when we were measuring using the spectrometer to measure the actual wavelengths from the filters, because the spectrum, okay, because the spectrum kind of looked like this, yeah, then you're going to have, we were taking the peak, weren't we? We were taking that as our value of wavelength. Then there's going to be photons of a range of frequencies going to be transmitted by the filter. Okay, but that would give us, if that was a significant source of error, then maybe our points wouldn't be fitting the line of best fit as closely. Okay, this is the answer. Right, the main one, it's all to do with, if you remember from the video when I set this up, I showed you that we should have been using something called a picoammeter, sorry, which can measure really small currents in picoamps, 10 to the minus 12. Now, unfortunately, our picoammeter is broken, so I made do with a simple multimeter set on the microamps. Now, that's going to have a big part to play here, because we measured the stopping potential when this dropped to zero. Okay, but let's think about the actual value of zero shown on the multimeter here. Now, because this can measure to the nearest 0.01 microamps, as soon as this hits zero, in theory, the current is actually 0.0005 microamps. That, in theory, is the current that you're hitting when this suddenly reads zero. So this is actually under. We should be going a little bit higher than this to get the actual current to true zero. So in my opinion, all the values of stopping potential are slightly under what they should be. And another thing with stopping potential is, okay, I had this set on the 2 volt setting, but I think we only went up to 0.8 volts, didn't we, for the stopping potential? We could have gone on to the next one. We could have gone up to, I think it was 2000 millivolts. We could quite have easily used that one, and that would have given us an extra decimal place of resolution in our values of voltage. So there you have it. There's my thoughts on the biggest sources of error. I think it's without question it's the values. There's quite a sizable systematic error in the values of stopping potential. Anyway, hope you enjoyed that practical as much as me. I'll see you in the next lesson. Thank you.